Space-based solar power is the concept of collecting solar power in space for use on Earth. It has been in research since the early 1970s. SBSP would differ from current solar collection methods in that the means used to collect energy would reside on an orbiting satellite instead of on Earth's surface. Some projected benefits of such a system are a higher collection rate and a longer collection period due to the lack of a diffusing atmosphere and nighttime in space. Part of the solar energy is lost on its way through the atmosphere by the effects of reflection and absorption. Space-based solar power systems convert sunlight to microwaves outside the atmosphere, avoiding these losses and the downtime due to the Earth's rotation. Besides the cost of implementing such a system, SBSP also introduces several new hurdles. Primarily the problem of transmitting energy from orbit to Earth's surface for use. Since wires extending from Earth's surface to an orbiting satellite are neither practical nor feasible with current technology, SBSP designs generally include the use of some manner of wireless power transmission. The collecting satellite would convert solar energy into electrical energy on board, powering a microwave transmitter or laser emitter, and focus its beam toward a collector on Earth's surface. Radiation and micrometeoroid damage could also become concerns for SBSP. History. In 1941, science fiction writer Isaac Asimov published the science fiction short story, Reason, in which a space station transmits energy collected from the Sun to various planets using microwave beams. The SBSP concept, originally known as Satellite Solar Power System, was first described in November 1968. In 1973, Peter Glaser was granted U.S. Patent number 3,781,647 for his method of transmitting power over long distances using microwaves from a very large antenna on the satellite to a much larger one, now known as a rectenna, on the ground. Glaser then was a vice president at Arthur D. Little, Inc. NASA signed a contract with ADL to lead 4 other companies in a broader study in 1974. They found that, while the concept had several major problems, chiefly the expense of putting the required materials in orbit and the lack of experience on projects of this scale in space, it showed enough promise to merit further investigation and research. Between 1978 and 1986, the Congress authorized the Department of Energy and NASA to jointly investigate the concept. They organized the Satellite Power System Concept Development and Evaluation Program. The study remains the most extensive performed to date. Several reports were published investigating the engineering feasibility of such an engineering project. They include resource requirements, financial, management scenarios, public acceptance, state and local regulations as applied to satellite power system microwave receiving antenna facilities, student participation, potential of laser for SBSP power transmission, international agreements, centralization, decentralization, mapping of exclusion areas for rectenna sites, economic and demographic issues related to deployment, some questions and answers, meteorological effects on laser beam propagation and direct solar pumped lasers, public outreach experiment, power transmission and reception technical summary and assessment, space transportation, discontinuation. The project was not continued with the change in administrations after the 1980 U.S. federal elections. The Office of Technology Assessment concluded that too little is currently known about the technical, economic, and environmental aspects of SPS to make a sound decision whether to proceed with its development and deployment. In addition, without further research, an SPS demonstration or systems engineering verification program would be a high-risk venture. In 1997, NASA conducted its Fresh Look study to examine the modern state of SBSP feasibility. In assessing what has changed since the DOE study, NASA asserted that the U.S. national space policy now calls for NASA to make significant investments in technology to drive the cost of Earth-to-orbit transportation down dramatically. This is, of course, an absolute requirement of space solar power. Conversely, Dr. Pete Warden claimed that space-based solar is about 5 orders of magnitude more expensive than solar power from the Arizona desert, with the major cost being the transportation of materials to orbit. Dr. Warden referred to possible solutions as speculative, and that would not be available for decades at the earliest. On November 2, 2012, China proposed space collaboration with India that mentioned SBSP, maybe space-based solar power initiative, so that both India and China can work for long-term association with proper funding along with other willing spacefaring nations to bring space solar power to Earth. Space Solar Power Exploratory Research and Technology Program in 1999. NASA's Space Solar Power Exploratory Research and Technology Program was initiated for the following purposes: perform design studies of selected flight demonstration concepts, evaluate studies of the general feasibility, design, and requirements, create conceptual designs of subsystems that make use of advanced SSP technologies to benefit future space or terrestrial applications, formulate a preliminary plan of action for the U.S. to undertake an aggressive technology initiative, construct technology development and demonstration roadmaps for critical space solar power elements. SERT went about developing a solar power satellite concept for a future gigawatt space power system, to provide electrical power by converting the sun's energy and beaming it to Earth's surface, and provided a conceptual development path that would utilize current technologies. SERT proposed an inflatable photovoltaic gossamer structure with concentrator lenses or solar heat engines to convert sunlight into electricity. The program looked both at systems in sun-synchronous orbit and geosynchronous orbit. Some of SERT's conclusions: the increasing global energy demand is likely to continue for many decades, resulting in new power plants of all sizes being built. The environmental impact of those plants and their impact on world energy supplies and geopolitical relationships can be problematic. Renewable energy is a competing approach, both philosophically and in engineering terms. Many renewable energy sources are limited in their ability to affordably provide the baseload power required for global industrial development and prosperity, because of inherent land and water requirements. Based on their concept definition study, space solar power concepts may be ready to re-enter the discussion. Solar power satellites should no longer be envisioned as requiring unimaginably large initial investments in fixed infrastructure before the emplacement of productive power plants can begin. Space solar power systems appear to possess many significant environmental advantages when compared to alternative approaches. The economic viability of space solar power systems depends on many factors and the successful development of various new technologies. However, the same can be said of many other advanced power technologies options. Space solar power may well emerge as a serious candidate among the options for meeting the energy demands of the 21st century. Space solar power satellite technology development at the Glenn Research Center. An overview. James E. Dudenhoer and Patrick J. George, NASA Glenn Research Center, Cleveland, Ohio. Launch costs in the range of $100 to $200 per kilogram of payload to low Earth orbit are needed if SPS are to be economically viable. Japan Aerospace Exploration Agency. The Tokyo-based Japan Aerospace Exploration Agency has been the subject of many previous studies and the stuff of sci-fi for decades. But space-based solar power could at last become a reality, and within 25 years. According to a proposal from researchers there, which is noted in the May 2014 IEEE Spectrum magazine, has a lengthy article, It's Always Sunny in Space, by Dr. Susumu Sasaki. JAXA announced on 12 March 2015 that they wirelessly beamed 1.8 kilowatts 50 meters to a small receiver by converting electricity to microwaves and then back to electricity. This is the standard plan for this type of power. On 12 March 2015, Mitsubishi Heavy Industries demonstrated transmission of 10 kilowatts of power to a receiver unit located at a distance of 500 meters away. Challenges. Potential. The SBSP concept is attractive because space has several major advantages over the Earth's surface for the collection of solar power. Collecting surfaces could receive much more intense sunlight, owing to the lack of obstructions such as atmospheric gases, clouds, dust and other weather events. Consequently, the intensity in orbit is approximately 144% of the maximum attainable intensity on Earth's surface. A satellite could be illuminated over 99% of the time, and be in Earth's shadow a maximum of only 72 minutes per night at the spring and fall equinoxes at local midnight. Orbiting satellites can be exposed to a consistently high degree of solar radiation, generally for 24 hours per day, whereas the average Earth surface solar panels currently collect power for an average of 29% per day. Power could be relatively quickly redirected directly to areas that need it most. A collecting satellite could possibly direct power on demand to different surface locations based on geographical baseload or peak load power needs. Typical contracts would be for baseload, continuous power, since peaking power is ephemeral. Elimination of plant and wildlife interference. Drawbacks. The SBSP concept also has a number of problems. The large cost of launching a satellite into space. Inaccessibility. Maintenance of an Earth-based solar panel is relatively simple, but construction and maintenance on a solar panel in space would typically be done telerobotically. In addition to cost, astronauts working in geo-orbit are exposed to unacceptably high radiation dangers and risk and cost about 1,000 times more than the same task done telerobotically. The space environment is hostile. Panels suffer about 8 times the degradation they would on Earth. Space debris is a major hazard to large objects in space, and all large structures such as SBSP systems have been mentioned as potential sources of orbital debris. The broadcast frequency of the microwave downlink would require isolating the SBSP systems away from other satellites. Geospace is already well used and it is considered unlikely the ITU would allow an SPS to be launched. The large size and corresponding cost of the receiving station on the ground. The possibility of energy losses during several phases of conversion from photon to photon back to electron, as Elon Musk has stated. Design. Space-based solar power essentially consists of 3 elements. Collecting solar energy in space with reflectors or inflatable mirrors onto solar cells. Wireless power transmission to Earth via microwave or laser. Receiving power on Earth via a rectenna, a microwave antenna. The space-based portion will not need to support itself against gravity. It needs no protection from terrestrial wind or weather, but will have to cope with space hazards such as micrometeors and solar flares. 2 basic methods of conversion have been studied: photovoltaic and solar dynamic. Most analyses of SBSP have focused on photovoltaic conversion using solar cells that directly convert sunlight into electricity. Solar dynamic uses mirrors to concentrate light on a boiler. The use of solar dynamic could reduce mass per watt. Wireless power transmission was proposed early on as a means to transfer energy from collection to the Earth's surface, using either microwave or laser radiation at a variety of frequencies. Microwave power transmission. William C. Brown demonstrated in 1964, during Walter Cronkite's CBS News program, a microwave-powered model helicopter that received all the power it needed for flight from a microwave beam. Between 1969 and 1975, Bill Brown was technical director of the JPL Raytheon program that beamed 30 kilowatts of power over a distance of 1 mile at 84% efficiency. Microwave power transmission of tens of kilowatts has been well proven by existing tests at Goldstone in California and Grand Basin on Reunion Island. More recently, microwave power transmission has been demonstrated, in conjunction with solar energy capture, between a mountaintop in Maui and the island of Hawaii, by a team under John C. Mankins. Technological challenges in terms of array layout, single radiation element design, and overall efficiency, as well as the associated theoretical limits, are presently a subject of research, as it is demonstrated by the special session on analysis of electromagnetic wireless systems for solar power transmission, to be held in the 2010 IEEE Symposium on Antennas and Propagation. In 2013, a useful overview was published, covering technologies and issues associated with microwave power transmission from space to ground. It includes an introduction to SPS, current research and future prospects. Moreover, a review of current methodologies and technologies for the design of antenna arrays for microwave power transmission appeared in the proceedings of the IEEE laser power beaming. Laser power beaming was envisioned by some at NASA as a stepping stone to further industrialization of space. In the 1980s, researchers at NASA worked on the potential use of lasers for space-to-space power beaming, focusing primarily on the development of a solar-powered laser. In 1989 it was suggested that power could also be usefully beamed by laser from Earth to space. In 1991 the Selene project had begun, which included the study of laser power beaming for supplying power to a lunar base. The Selene program was a 2-year research effort, but the cost of taking the concept to operational status was too high, and the official project ended in 1993 before reaching a space-based demonstration. In 1988, the use of an Earth-based laser to power an electric thruster for space propulsion was proposed by Grant Logan. With technical details worked out in 1989, he proposed using diamond solar cells operating at 600 degrees to convert ultraviolet laser light. Orbital location. The main advantage of locating a space power station in geostationary orbit is that the antenna geometry stays constant, and so keeping the antennas lined up is simpler. Another advantage is that nearly continuous power transmission is immediately available as soon as the first space power station is placed in orbit. Other space-based power stations have much longer startup times before they are producing nearly continuous power. A collection of LEO space power stations has been proposed as a precursor to geospace-based solar power. Earth-based receiver. The Earth-based rectenna would likely consist of many short dipole antennas connected via diodes. Microwave broadcasts from the satellite would be received in the dipoles with about 85% efficiency. With a conventional microwave antenna, the reception efficiency is better, but its cost and complexity are also considerably greater. Rectennas would likely be several kilometers across. In space applications, a laser SBSP could also power a base or vehicles on the surface of the Moon or Mars, saving on mass costs to land the power source. A spacecraft or another satellite could also be powered by the same means. In a 2012 report presented to NASA on space solar power, the author mentions another potential use for the technology behind space solar power could be for solar electric propulsion systems that could be used for interplanetary human exploration missions.